Okay, this lesson we're going to look at the normal distribution a little more in detail than we have in the past. So just some characteristics that we saw from a discrete distribution in an earlier lesson. The sum of the probabilities was 1, and each probability is between 0 and 1. Right? We looked at binomial, we looked at discrete, binomial being an example of a discrete. And continuous distributions we're going to look at here. The total area under the curve is 1. We've seen that in an earlier lesson. And every point on the curve must have a vertical height greater than or equal to 0. Right? So when I've got my curve, my normal distribution, this is for any continuous, but we're going to look at specifically the normal. The area, if I were to sum up the area of that under that curve, that's going to be 1. And I'm never going to have the line do something like this. Okay? It's never going to be negative, right? It's always going to be above 0. Each vertical height's above 0. That's what that means. Okay, the normal distribution officially looks like this. I mean, we know the picture value, what it looks like, but here's the formula that will actually generate that. Looks a little bad, doesn't it? The good news is that we're going to use the calculator for most of this. A couple of examples of normal distribution. We see here, so the women have a mean of 63.6, so the mean is going to go right here in the middle, the height of that, and standard deviation of 2.5. I will usually write that right below, just so I can see that as well as with this one. So men, mean of 69.0, standard deviation of 2.8. Okay, so when standard deviation is smaller, it's going to be a little more pulled in. This one's a little wider, right, because it's got a larger standard deviation. Not that much wider in this case. Now notice the mean at 69 is not taller than that. It's shifted over on the right, all right, because the mean there's my x-axis there. The mean goes along this. As I get further to the right, I get a larger mean. So example 1. The lengths of human pregnancies are normally distributed with a mean of 266 days and standard deviation of 16 days. Draw and label a normal curve with the parameters labeled. I didn't always used to make students draw this out, but students who didn't draw it out universally missed it. And students who did draw it out almost always got it right. So let's draw this thing out. It helps us think about it. So I'll draw it up here. So here's our normal curve. Doesn't have to be perfect. Our mean right here, 266. Standard deviation of 16. And we can go ahead and fill this out, right? We can go 1 standard deviation to 3 standard deviations is usually pretty standard to pull this out. Okay. And I've already drawn this out for us right here. So just use the calculator and add 16 3 times and subtract 16 3 times. Now in earlier lessons I would ask you to find the percent that would fall between 250 and 282. But now we're going to be able to, we'll see shortly, that we can find any values on here. So let's shade the region that represents the proportion who are less than 245 days. So 245 about right here, right? And we're just going to shade right there. Okay, we'll go ahead and pencil in 245. I think I actually got this shaded. There we go. A little more official. Suppose the area was found to be 0.0947. So suppose I crunch that out and that turned out to be 0.0947. What does that mean? Provide 2 interpretations of this result. So one interpretation is that the proportion of human pregnancies that last between, or actually that are less than 245 days is 0.0947. That's about what? Roughly 10%. So about 10% of pregnancies will last less than 245 days. Another interpretation is that if we randomly select a human pregnancy that's 245 days or less, it's going to be that the probability of randomly selecting a pregnancy out of all the pregnancies is 0.0947. So a couple different ways to look at this, looking at more from a probability standpoint or from a proportion standpoint. Example 2. Data set below are heights in inches of 80 randomly selected 5-year-old females. Use StatCrunch to create a histogram with the normal curve superimposed on top. Do you think the normal curve accurately describes the height of 5-year-old females and why. Okay, let's go ahead and go to StatCrunch. This is actually 7.1, number 38 from the Sullivan text. If we're still using that one while you're watching this, we can go ahead and move over here and look at this live. Here's 7.1, number 38. Go ahead and pop on that. Otherwise, you can just enter the data in, or I may provide the data set for you. It's already in here. Let's create a histogram. So we'll go to Graphics, choose Histogram. We're lucky we just have one variable, so it's pretty easy. I'm not going to group or anything. Click Next. Let's do relative frequency. And no, we don't need to do that. Click Next. And we will overlay the normal distribution on here. I don't think you have to give it a mean standard deviation. I think it goes ahead and does that for you. So go ahead and click Next. Next. And create graph. And there we go. There it is right there. Okay, so we have the normal distribution here. It looks like it does a pretty good job of fitting that. And later on, we'll look at ways to sort of test for normality visually. And there's one numerical measure that allows us to do that. Okay, so there's the output there in StatCrunch. Okay, example 3. The graph of the normal curve is given. Use the graph to identify the value of mu, which is the mean, and sigma, which is standard deviation, right? So again, there's my mean, and here's my standard deviation. Okay, hopefully this is not too bad. What's the mean? It's 100, right? There's my mean right there. What's the standard deviation? 10. I usually put that right below it in parens. So every 10 units, I've gone over. Okay. So the standard normal curve. So the standard normal is the normal probability distribution that has a mean of 0, standard deviation of 1. When we plug that back into that nasty formula we had, it reduces to something a little bit less intimidating. E to the negative 1/2 x squared divided by 2 pi. Again, we're not going to be using this formula to crunch these out. You would use that in upper level stats class. We're going to use the calculator. So find the area under the normal curve between z equals 1.5 and z equals 2.5. So another way we could have written that is p, the probability that z is in between 1.5 and 2.5. And I'll be honest, we don't really worry about if it's equal to or not. It doesn't really matter. So we're going to draw, label, shade, and probably add one more. Compute. Draw, label, shade, compute. Okay, so we went ahead and drew this out. We have a mean of 0. You don't need to worry about the vertical axis here. Mean of 0, and just kind of draw it out 3 to the right 3, to the left 3. And we're going in between 1.5 and 2.5. What is that area? About 0.0659 or 0.061. Not too picky on the round. You usually take it out at least 2 or 3 decimal points. So again, our syntax here, you go to normal CDF, left, comma right, comma mean, comma standard deviation. Let me do that one live for you. I'll do a few of these live, just so you can see where that's even accessed. So that's accessed under the distribution menu. Pull this out a little bit. So if I go to second distribution, I'm going to go to normal CDF, right? And then I'm going to go left bound, so the left bound number, comma, right bound number, comma, the mean, comma, standard deviation. Won't let me use the print on the keyboard, so let me close this in. Okay. And there we go. So this is a very nice way to crunch this out. We used to have to use tables for this, and I'll show you one example later of how to use the tables that are in the back of the book, but we pretty much don't use that now. We'll use technology to crunch this out. Okay, see if you can do this one on your own. Suppose we have a mean of 0, standard deviation of 1. Use the calculator to find the probability or area, another way to look at it, when z is greater than 1.96. Draw a label shade and compute. Okay, so pause the video, see if you can get this one to come out. Alright, welcome back. So what do we got here? Here's our curve, label it out. We're looking at just almost from 2 on, and what do we get? About 25%. Or, sorry, about 2.5%, 0.02499. Let me show you how we can use StatCrunch to crunch these out. Let's see if I can pull that up. Here we go. If you click on Stats and go to Calculators, we can click on the normal distribution. It doesn't really work very well when you have something in between, but if you're just going less than or greater than, it works really well. So we can do, what did I say, 1.96, and we're doing greater than 1.96, and there we go. We get exactly the same thing. Gives us a nice shade there as well. If you want to copy that, I think you can click Snapshot, pop it to the clipboard. We're not going to worry about exporting that, but you can if you want. Okay, again, pause the video, just getting practice putting these into the calculator. Probability that z is between 0 and 1.44, and part B between -1 and 2.13, to the right of 1.5, to the left of 1.5. And so I definitely recommend drawing out. I know it takes an extra 15 seconds, but draw out and label your normal distribution. It'll really help you get an understanding of what you're finding, and if you happen to put it in the calculator incorrectly, it'll hopefully be relatively obvious that you've messed something up. All right, welcome back. So here's our first one: normal CDF 0, 1.4, 1, between 0 and 1.44. Okay, B between -1 and 2.13. Very similar. -1, 2.13. Again, remember our syntax is left bound, right bound, mean, standard deviation. To the right of 1.5. Okay, and again, I probably should have explained this before in the last example. 1.5 comma, and then I put 1E99. Let me show you where that is on here. Okay, so again, I'm going to go second distribution, normal CDF, and we're going to the right of 1.5. So if I draw a little picture right here, it doesn't have to be an elaborate picture. There's Z of 0. Here's 1.5. I'm going to the right of that. So that's all I mean by picture. You don't have to put all the standard deviations on there. Just put the ones we care about. And so I'm going from 1.5, which is my left bound, sure what happened there. So 1.5, comma, and then what's the right bound? Well, the right bound is infinity. Now, you can do one of two things. You can put a really big number here. I mean, you could put 30, and that's certainly big enough to take care of it. But just to have something uniform, I always put, for infinity, 1 times 10 to the 99. That'll guarantee it. If you put something, bigger relative than 1.5, if you put 10 even, it would give you the same answer, I think. Put 1,000 if you want. But 1E99 will always work, comma, the mean, comma, standard deviation. If you happen to flip those around, it'll let you know on this particular one with the standard normal. There we go. Now we can actually get the calculator to graph and shade this for you. For some students, this is helpful. I'll show you that on the next slide, some details on how to get it to do that. And let's do this last one to the left of 1.5. To the left, again, if I'm drawing that out, what's that going to look like? So just a quick sketch here. I'm to the left of 1.5. There's 0. Here's 1.5. I'm to the left of that. So my left bound is this negative infinity. And so negative infinity is negative 1 times 10 to the 99. Okay? So just you could have put negative 1,000, you get the same thing in this case. But if the mean were 1,000, standard deviation of 500, you couldn't put that. So just to put something relative, you got to put something out maybe 5 standard deviations from the mean at least, to the left or right. So we get about 0.933. So for those of you interested in looking how to have the calculator graph this for you, you go to Ch7 Normal. Let me see if I can follow this with here. I don't do a lot of this, but one of my students I think pointed this out to me, so I wanted to share it with you. And we get there, I think it's with the draw command. No. Distribution, scroll over to draw. Ch7 Normal. So we go Ch7 Normal. And we put our same parameters in. So we're going to do 1.5, comma, this is the C part I think, 1 E99, comma 0, comma 1. You may need to make some window adjustments. If I go ahead and click enter here, I've still got some stuff I need to clear out, right? Let me turn off my stat plot because this is not a stat plot. So turn all that off, and that happens to me. It happens to me all the time. So don't freak out if something like that happens. Just so recognize, oh, my stat plot's still on. I don't make sure my y equals is cleared out. Go back to the home screen. You can press second enter. Pulls back up the last thing you did, and press enter again. And we don't see anything. That's because my window's all messed up. I need to adjust my window. So this is where it's sort of important to sort of know something about your curve. And if I were to draw that out by hand, I've got 0, and I'm looking at shading normal from 1.5 to infinity. So I need to make some adjustments to my window. So press window. Right now my window's set at 92.6. I guess the last thing I graphed. So x min, you know, we want to go at 3 standard deviations. That's going to be -1, -2, -3. So let's make x min -3. Make x max, make it +3. That's fine. X scaling, I usually make this whatever the standard deviation is. It'll put a little notch. You don't have, it doesn't really matter what this is, but it'll put a little notch every 1 standard deviation, because standard deviation is 1. The y min, you can make it 0 if you want, but I like putting a little bit of height under there so I can see some of the labels. So maybe -0.3 in this case. Sorry, I've changed the wrong one. That should be 1. That's -0.3. And then the y max, you know it can't be more than 1. Let's just make it a 0.5 and see what happens. It must look good because I've got it right there. Now press graph. Let's see what we got. Actually, I've got to go back to the home screen and do this again. So second enter and then pull it back up. And there we go. And I get the same thing. And it even gives me the area here. So the low is from 1.5, the higher is from 1 E99, which is infinity, 0.0068. Exactly the same thing I got doing this by hand. For me, it's a lot of work to do. Maybe in the beginning you ought to do a few of these like this. It's certainly up to you. Okay, let's do a few more. Going back the other way now. So find the value of z that corresponds to the given area. So now we want to find the z-score that corresponds to this area. In the old days, we used to have to look this number up in a table and back out the z. But we don't do that anymore. We're going to use another command. It's the inverse normal command. So again, it's under distribution, and number 3, inverse norm. So we're going to put our value, 0.0166, comma, the mean, which is 0, comma, standard deviation, which is 1. And then press enter. So this corresponds to a z-score of about -2.13. That should be what I got here. I've got little screenshots here so you can have for your notes. Okay. And again, remember what the z-score tells you. It tells you the number of standard deviations from the mean. Okay, example 8. Find the value of z corresponds to this area. Pause the video, see if you can do this one. Now here, you may have missed it. What that inverse normal gives you is it'll give you the z-score that corresponds to the area to the left. That's the value it's going to give you. When you put that area in, it's assuming you're putting that area in. I mean, how else would it know? So you can do one of two things. You can know that my z has to be negative the way it stands here. You can visually see, right? It's a z is going to be negative to the left of the mean. So you can just put that number into the inverse norm, and whatever value you get for z, you know it's going to be negative. Or, how do we find out this area? If I put this area in, I can just put that area in, and I'll get the correct z-score. Well, if this area is 0.8962, what's the total area under the curve? What is it? It's 1, right? That was one of our first properties we looked at. So I can just do 1 minus 0.8962, and then put whatever I get there, put that in to the inverse norm. And I think that's the way we're going to do it. Yeah, 1 minus 0.8962, we get 0.1038, and then do you inverse norm that. Again, you could have inverse normed this number. You would have gotten a positive 1.26, but then you know you have to make it negative. Just from visually, we can tell it's got to be negative. I prefer you do it this way I showed you here. Certainly up to you. I'll never know. Okay, find the indicated z-scores. Be sure to draw and label the normal curve. So find the z-score such that the area under the standard normal curve to its left is 0.088. Couldn't read that number. And then for part B, find the z-score such that the area under the standard normal curve to its right is 0.10 around the 2 decimals. Okay, pause the video here, see if you can get these two done. All right, welcome back. I don't have these drawn out for you already, so I'm going to draw them out. So we'll do part A. So find the z-score such that the area under the standard normal curve, or standard normal is our normal distribution with a mean of 0, sigma of 1. So find the z-score such that the area under the standard normal curve to its left is 0.088. So to the left, 0.088, we know from 0 to the left is 0.5, right? So the mean splits the normal curve in halves, right? So I know it's probably somewhere over here. So that area is 0.088. So let's crack out the calculator. And we will do second distribution. Whoop. Second distribution. Try that again. Second distribution, inverse norm. 0.088, comma, 0, comma, 1. We get a z of negative 1.35. That is rounded to 2 decimal points like I asked. Okay, how about part B? Find the z-score such that the area under the standard normal curve to its right is 0.10. Again, don't spend a lot of time on drawing these curves out. Doesn't take but a second. That area there is 0.10. We're looking for the z right here. So if I put in, let me show you this, I mentioned it earlier, but if I put in inverse norm number 3, and if I just put in 0.10, comma, 0, comma, 1, it gives me a negative 1.28. But we can tell this is not a negative 1.28. It's got to be positive, so it's the positive 1.28. Now, why did it give me a negative? Because remember, it gives me the value to the left. It always gives me this value over here. Okay, whatever that value happens to be. So, what do I need to find? I actually need to put in this area. If this is 0.10, this has got to be 0.90, right? So I can put in second, well, I can just actually go second enter and change that from 0.1 to 0.9. and then put enter. 1.28, which is what we have down here. So again, z was 1.28. You have no idea how much easier this is using the technology as opposed to having to use tables. Okay, so we were able to do this whole unit in one day, 1 or 2 days, as opposed to spending a whole week and a half on it. All right. So now let's look at some applications. And because we have the calculator, we really don't have to worry so much about the standard normal, but we need to go through that process just for you to get a sense of how to compute these out. The good news is they're exactly the same way when we look at applications. Again, we're just going to use the normal CDF. So one way you could do this is convert all of our scores, all of our values, we'll see in a second, to z-scores, and then use normal CDF, or use tables if you're so inclined. I'm going to really encourage you to use normal CDF, though. Okay, so assume that adults have IQ scores that are normally distributed with a mean of 100, standard deviation of 15. Find the probability that a randomly selected adult has an IQ between 110 and 120. Pause the video, see if you can draw this curve out, label the mean, and the relevant x values. Again, you don't have to put all the x values on there, just the ones we really care about. All right, welcome back. Pause it. Did you pause it? I know not everybody paused that video. That's okay. Here we go. So we have these numbers on here. So we have the 100, and we want between 110 and 120. I'm going to show you the way we could have done this. Okay, so don't write these down. We used to have to convert these to z-scores. So we'd find the appropriate z-scores. So this 110 was 0.67 standard deviation from the mean, and then this 120 is 1.33. We would then look these up in a table. Okay, and then we would subtract them and get 0.1596. But we're not going to do any of that. All we're going to do is use this normal CDF. 110, comma 120, comma, again, our mean, comma, standard deviation. Before, with the standard normal, the mean was 0, standard deviation of 1. But now with applications, which is what we're going to be working with in every other problem, we're going to have most likely a different mean and standard deviation than 0 and 1. In our case, we had 115. So again, this area, or the probability, is 0.16, or 0.1628. 0.16128. So a little bit different than the table, right? Because there was some definite rounding when we use the table. Not as much rounding when we use the calculator. It's a little more accurate. So if we draw this out, we can draw it out again, and we get the same thing. And here's a rule of thumb. If you're wanting to get a sense for how to adjust that window, you can put this on your note card if it helps you. Define the x-min is the mean minus 3 standard deviations. X-max, mean plus 3 standard deviations. We went through there. We did that before. I told you that scaling was standard deviation. And y-min and y-max, I didn't really tell you. The y-min, I like having y-min rather than 0, because I want a little bit of room for it to give me this area. To give me these values. So it's not covering up the graph. And so anything below 0 just a little bit, kind of depends on how big your values are. And y-max, I usually make it at 0.5, 0.4, 0.3, just to see how you get a good looking curve. 1 over 2 times standard deviation, it usually gives you a good one. And the y-scaling, I don't worry about that. Okay, example 11. Find which IQ score separates the bottom 80% from the top 20%. So we are looking for the 80th percentile, right? So this is back to our percentile, 80th percentile. So what are we going to use here? Inverse norm, right? If you know the probability, or if you know the area, you're going to go to inverse norm. If you're looking for the probability, you're going to use normal CDF. Once you do, a handful of these, half dozen of these, that becomes quite evident. So inverse norm, again, it's the probability, comma, the mean, comma, standard deviation. If you mess this up, it'll usually spit something out at you. It won't like it. You could actually switch to mean standard deviation, but you should get a number that makes no sense at all if you do that. So 112, and that makes sense. So I mean, if we didn't have that drawn out and we happen to switch them, you may not have a sense for what it is. So always draw these out. Okay, on the test, I'm going to count off if you're in my class and you don't draw these out, and I tell you to draw it out, draw that out. Example 12. Consider babies born in the normal range of 37 to 43 weeks gestational age. Extensive data support the assumption that such babies born in the U.S. Birth weight is normally distributed with a mean of 3432, standard deviation of 482, and this is in grams. So what is the probability that the birth weight of a randomly selected baby of this type exceeds 4,000 grams? Draw, label, shade, compute. Good, I had that compute on there. Part B, what is the probability that the birth weight of a randomly selected baby of this type is between 3,000 and 4,000 grams? Draw, label, shade, compute. And then how would you characterize the most extreme, both the high and the low, 0.1% of all birth weights? Draw, label, shade, compute. Okay. And I should have had a question mark there. Okay. Go ahead and see if you can do part A. So parts A, B, and C, we've done these before, so you want to be able to eventually do these on your own. See if you can pause the video and do one of these. It'll really, you doing these before you watch me do them will really help, rather than just writing them down. Now, writing them down and watching me do them, it helps to some extent, but you making those mental connections yourself, making a mistake here or there, then me kind of filling in the gaps is really what's going to help you learn this, as well as our in-class material, if you're in the in-class class. Okay, so here we go. I've drawn. I've labeled. Now I want to shade, so we're looking at what's the probability that the birth weight of a randomly selected baby of this type exceeds 4,000 grams. So 4,000, you know, just somewhere in between there. And exceeds means we're going to be shading this way. Now why we do all this is it helps me minimize my think time. I don't want to think about all that when I'm putting this in the calculator. Okay, so what are we going to do here? We're looking for a probability, so it's normal CDF. Left bound is 4,000. Right bound, you could put anything super big, put a million in. I always just put in 1E99, just as easy. And then we're going to put our mean, 3432. And standard deviation, which I should have written down there, is 482. And press enter. So I should have put that down as part of my label here. Standard deviation is 482. So I get a probability here of 0.1193. About 12% if we're going to convert this to a proportion or percent. And there's the snapshot there for you. Okay, part B. What is the probability that the birth weight of a randomly selected baby of this type is between 3,000 and 4,000 grams? Draw, label, shade, compute. Now once you've drawn it once, it's pretty easy just to recopy that. I recommend recopying it, and I know it takes an extra 15 seconds, but it's worth it. Okay, so hopefully the shading here is going to be okay. We're going to shade between 3,000, so just above that, and 4,000. It used to be more important that we drew this out because we were using tables, but it's still pretty important that we get a sense for what we're trying to figure out. So we're looking for this area here. I'll assume you can put that in, left bound, comma right bound, comma mean, comma standard deviation. Again, our standard deviation is 482. There's my shading again, and I get about 0.6956, about 70%. I forget what I told you around to, maybe 4 decimal places. 0.6956. Okay, I meant to have this fly up, but you got it right here. How would you characterize the most extreme, both the high and low 0.1% of all birth weights? Draw, label, shade, compute. So we still label that. Again, we're looking at 0.001, so somewhere right in here, right? So again, that's 0.001, because it's 0.1%, right? So it's 0.001. And And the same on this side. Again, that's 0.001. So for this side, I do 0.001 is inverse norm, because we're actually looking for the value, comma, mean, comma, standard deviation. Again, remember your syntax. So inverse norm. So probability, comma, mean, comma, standard deviation. And we get 1942, and that looks about right. So they're about 1942.5. And the other one, I do 0.999, because if I did 0.01, I get that value again. So this one's it is important to go ahead and subtract out, right? To do 1 minus that. Because I don't have a nice balanced symmetric 0 and positive and negative, so I've got a mean that's not 0. So I do 0.999, because I actually am looking for all of this value here, which is 0.999, and that'll give me that value right there, which is what I want, 49.21. So babies that weigh less than 1942.5 grams and more than 49.21.5 grams are in the extremes, the 0.1% of all birth weights. And just kind of remember, to put this in context, about the conversion from grams to pounds. 1 pound is about 454 grams. So 1 pound is about 453.6 grams. So you can just divide each of these by 453.6 to get a sense back in pounds if you're used to working with pounds rather than with grams. Example 13. Replacement times for TV sets are normally distributed with a mean of 8.2 years, standard deviation 1.1. Find the probability that a randomly selected TV will have a replacement time less than 5 years. And then part B, if you want to provide a warranty so that only 1% of the TV sets will be replaced before the warranty expires, what length of time should be the warranty be? Okay, so you can pause the video, draw these out. All right, welcome back. So let's draw these out. Okay, so here's my first one. Let me get this calculator out of the way. So I'm looking, I've got a mean of 0.82, and again, I should have written down sigma is 1.1. Probably should put years there, but I think we know the units. I'll worry about those at the end. And I'm looking for this probability right here. So I want TV sets to be replacement time less than 5 years. So what's that probability? Normal CDF, again, negative infinity, comma 5, comma 8.2, comma 1.1. And we get 0.00118, 0.002 if we wanted to. Don't tell you what to round, so 0.2% of my TV sets have a replacement time less than 5 years. Now let's say we want to provide a warranty so that only 1% of the TV sets will be replaced before the warranty expires. What length of time should be the warranty be? So again, let's draw this out. I'm actually looking for this value here. What is that value there? Draw your normal curve. We're doing inverse norm. About 5.6 years, so maybe 5. Practically you wouldn't want to offer a warranty for 5.64 years. People would think something's up. So somewhere between 5 and 6 years.